Hi, welcome OpenFoamers. Welcome back. So in the last video, we were talking about this thing called unstructured meshes. So let's say you have two cells like that, and you have some quantity over here. For example, it could be velocity, it could be temperature, or it could be a convective flux. And what is a convective flux, you might ask? So convective flux is basically so if you look for example, at the heat equation, right? So this is actually a standard kind of transport equation where the accumulation in the cell plus the convection in and out of the cell is equivalent to the diffusion term and the source term. So if we want to bring that down to something more concrete, we can take a look at, for example, the energy equation in the chtMultiRegionFoam, where it is solved for the energy equation. Okay, where's that convection? Yeah. So for example, you have some internal energy that you want to conserve. This term here, this equation I'm highlighting, is the change of the internal energy in the cell, in the control volume, or in the infinitesimally small volume. And then this del by del xj, this is this is the convection term. So we were talking about divergence before. This is where this really comes in. Del by del xj is a short form of how you write okay, by del, let's say you have del by del xj. All right, and here says rho uje. Okay, rho uj j e. Okay, what is this actually? This means it's a vector representation of a del by del x. Okay, del by del x, rho u e, and then you have this is representing the x equation. Then you have all the terms in the x equation, the y equation, okay, and the z equation. Rho, okay, this one should be a v, right? Rho v, rho we. So normally, we will either have a scalar or vector equations. Okay, scalar or vector equations. When you write this term del by del xj, it just means the derivative with respect to position in the x, y, and z direction, or in the 3 coordinate direction, r theta z or r theta phi, depending on which coordinate system you are using. So these are what you call the convection terms, where you see there's a rho u and e, and rho u is what we usually call phi, and this is the mass flux. Okay, this is the mass flux, which we will usually see over here. Okay, of course, we may not always use phi to represent mass flux. It can also mean a velocity flux, but it may mean velocity flux as well. So when you see in your fvSchemes, you have phi u, phi k, phi h. These are talking about the mass flux. Okay, rho u. So yeah, this actually talks about the x, y, and z directions. When you see phi here in the fvSchemes, it talks about the mass flux, where it's rho times u. Okay, so this is the rho times u you see in your fvSchemes. Alright, so the rho and U can carry along some internal energy, it can carry along some enthalpy, some kinetic energy, blah blah blah. So this is what it's talking about. Of course, this phi here is actually different. The phi here can mean, of course, in the OpenFoam documentation, phi means whether it could be a U, it could be a K, it could be a H, it could be small letter k, it could be epsilon, and all these other things. So it is the quantity that is being carried along by the velocity. For example, it could be enthalpy, it could be internal energy, etc., etc. So just be careful. I mean, the nomenclature and the way we define variables can be different, but in this case it means, yeah, this there is some property, some scalar, for example the enthalpy or the internal energy, which we are carrying along. Okay, so if it's the enthalpy we are measuring, this is likely this equation is likely to be thought of as what they call that, energy equation. If it's a Navier-Stokes equation, over here, we can see that this is actually a momentum equation. So instead of enthalpy being carried along, it is a momentum that's being carried along, or some kind of velocity that's being carried along. So it's slightly different, okay? But this is what this equation talks about, and the numerical scheme to solve this equation is the Gauss scheme, which we were discussing in the last video. And as said before, we could have some quantity here. There's a phi in cell 1, phi in cell 2, okay, and then there is some phase property. We want the phi of the phase. Alright, now to guess what the phi of the phase is, we could use a linear interpolation scheme, which will then kind of guesstimate the phi of the phase, probably somewhere around here. Okay, somewhere around here, and that will probably be the wrong phi phase, right? So this is the phi phase interpolation. Let me write that properly. Phi phase interpolation. Okay, so keep this picture in mind when we talk about the fvSchemes. So, I mean, as with every linear interpolation, that you could find yourself in a very precarious situation, because there's such thing called a stiff equation. And what stiff equation does is that, okay, if stiff equation means that if we extrapolate the what do you call that, the value, which is changing with time. So let's say you have some time varying quantity or distance varying quantity, and which is an ODE, and we want to use some numerical way to solve it, for example the Euler way. Now the thing about stiff equations is that you can have this thing called oscillations. So you can see in this Wikipedia page, if you use the Euler scheme, where it's a linear interpolation, or linear way of guessing the gradient, so as to plot out the value over time, the time varying value, whatever this value is. So you can see the actual line is this cyan color. But if we use linear way of solving this ODE, you can see the values oscillate, which is pretty much quite similar to what is being presented inside our OpenFoam cases. So we see the value blow up. Okay, so for example, we have the Euler scheme, at h equals 1 over 4, and then okay, so we see the value blow out of proportion, just like our temperature was supposed to be, you know, between 400 and 300, but instead the temperature shot all the way negative, and then the maximum temperature also shot beyond 400 Kelvin or 500 Kelvin, when our 500 Kelvin was our maximum temperature. So I mean, there is actually one way that to prevent this from happening. Okay, so we know that linear, you know, gas in a stiff equation, such as what you saw just now, and also the case where you have small meshes, we do have this kind of problem happening. So again, we have 2 points, we have point 1 and point 2, and then we have the phase. We have the phase value. So let's say point 1 is here, point 2 is here. Okay, so if we were to interpolate, so the phase value will be somewhere here. Okay, so this is the quantity we want. We can just call it phi. Okay, so this is not exactly the flux, or maybe I can just use the term y instead, just to avoid confusion. So let's say this is y and this is x. Very classical graph formula. So if you want to interpolate this phase value, this is a linear scheme, all right, of interpolating. However, we know that using this linear scheme, it could very well generate points. It could generate data points which are really off, as you can see in this stiff ODE kind of a thing, and that can be a problem. So the way of dealing with that is called something I'd like to introduce to you, called the Upwind Scheme. So Upwind Scheme is over here in the Divergence Scheme. Okay, so this is where you'll find it in the OpenFoam. And in the PowerPoint presentation that Move Dynamics has put, the Upwind Scheme is shown here. Alright, so I will just quickly draw on Paint what it looks like. So for the Upwind Scheme, you, instead of linearly interpolating this phase point, one would say, okay, let's not do any interpolation at all. Let's just say that the value of the phase, okay, the value of whatever we are calculating, it could be enthalpy, it could be some flux or whatever, the value at this phase here will not be this linearly interpolated value. Instead, it will be the value of the cell adjacent to it. Okay, so that's why we call it upwind. It is the value of this cell 2. So in the Upwind Scheme, so this is a linear scheme. Okay, all right, never mind. Yeah, in the linear scheme, you will have this case where you try and linearly interpolate the value, the y value in this case. In the Upwind Scheme, we try and get rid of the interpolation altogether. Instead, we just say that the value of the phase is the value of, the value of the quantity, let's say y at the phase, is the value of the quantity y at the second cell. So that is what Upwind Scheme is all about. So this is what you basically see here. So according to this PowerPoint slide, they say that the scheme is bounded, non-oscillatory, and diffusive. So if we take a look at Where is this? Yeah, you take a look at this. It says it's a first order and bounded. Why is it bounded? It is because let's say, yeah, it's because we get rid of the interpolation altogether, and instead we say that, okay, the value here is the value, the value here is the value at the cell, and we don't do any interpolation, and that's why it kind of forces the value to get within a certain value. Okay, so this is what Upwind Scheme is. So usually linear schemes can cause some instability, and where this is shown in this slide is over here. Okay, you can take a look on your own, but you can also see it inside this inside the OpenFoam user guide. Okay, so there will be some examples. There are actually some examples of it, and you can see where the examples are over here in this examples tab. Okay, under the schemes or divergent schemes. Okay, so you have seen a divergent scheme example, and what is the scheme over here? Well, you see, this is a case setup. You have some very randomized mesh, and you take a look at this mesh. It looks pretty much uniform. It's not a square shape, but you have a very even distribution of the mesh size, and you don't have too much offset or also non-orthogonality. You don't have meshes that are oriented, or you don't have cells that are oriented in a very awkward way to one another. Okay, and over here you have left, bottom, right, and top boundaries, and the velocity u is like carrying some quantity up to the top right hand corner. Okay, so these are the boundary conditions. So the velocity is set to a value of 110, which is 1 in the x direction, 1 in the x direction, 1 in the y direction, so it's going to the top right. So the right and the top, the boundary conditions here are 0 gradient, so that's basically just letting the flow come through. Okay, front and back's empty, meaning to say it is a 2D simulation. So this one is called passive scalar, is initialized to 0, and you evolve with the velocity by assigning 1 at the left boundary. So what is it here? It could be some temperature, normalized temperature. So at the left we have a value of 1. Okay, it could be temperature, it could be some concentration of something. At the left it's 1, at the bottom it's 0. So if in theory, if there's not too much diffusion, the thing should be split up like so. So you have a case where you have flow coming this way, and then you have some scalar. We can use the y to try and say what the scalar is, and then y will be 1 at this boundary, 0 at this boundary. Y equals to 0. Okay, y equals to 1. So if the velocity is bringing like this direction, bringing y in this direction, only the top half of the triangle should be, or the top left half of the square should be filled with y equals 1. Okay, so that's what the test case is like. So if we have the Upwind scheme as I was showing earlier, yes, you will have a very steady solution. However, there is some you actually get some of the y, or some of the scalar actually diffusing itself onto the other side. You see, it's not a very clear-cut line, between this side and this side, but you know, the thing is that the quantity kind of diffuses itself. It's as if there is some diffusion process that causes whatever quantity here to diffuse from this side to this side. Okay, so the linear scheme is what we were talking about earlier, where we have at the face we try and interpolate the value properly. However, I told you there was some instability that's associated with it, and we can see here. Okay, we can see here. All right. Okay. Yeah, we can see here in this one I'm highlighting. You can actually see some wavy things here. Okay. So it's very similar to the stiff ODE problem I was telling you about before. And let me bring this here and I zoom in so you can see. So you can see when at these corners here, there'll be some of these wavy conditions happening. Okay, and these instabilities can actually grow. So this is instability with respect to x. So it is instability with respect to some normalized distance. Okay, so we see that there is some of that instability over there due to the linear what do you call it, linear scheme, and you can see this kind of ripples going across from the center line. So it does prevent this diffusion effect from happening, but you can see these ripple lines. It's not accurate, and well, this kind of conforms to the actual solution a little better. In some cases, we might actually get a solution blow up, as we saw in our case. So the better one is to have the stable solution like this upwind case, where at least the solution is bounded between 1 and 0. You can see this. You can see this thing here. These values here. When they are mentioning bounded, you see that the values of the upwind scheme, whether it's using this quad or tri whatever thing, doesn't really matter. You see this thing actually never exceeds 1. Okay, never exceed 1, right? But you see this one actually exceeds 1, right? So it exceeds 1, and over here it drops below 0. And here it doesn't drop below 0. So you can see that different schemes, they kind of give you different errors associated with the scheme. So you kind of want a scheme that's the best of both worlds. So they call it there are a bunch of schemes that try to do that. So you can see here the remaining methods provide a blend of first order upwind and second order linear methods. So we have the Minmod scheme. Okay, Minmod scheme. And okay, I'll just open the Upwind Scheme tab for reference. Okay, I mean, there's not too much info here except this normalized diagram, but of course it's easier to see the schemes over here, what its effects are. The other one's the SCFD. Then we have limited linear. Now this one's quite interesting. Limited linear is basically the linear scheme. All right, it is the linear scheme, but they try and limit the variable from going too out of the bounds. I mean, over here it says it's unbounded, but it tries to introduce some stability. Okay, and this is the result you get. Vanilla scheme also tries to introduce some stability, limits the diffusion problem that is very associated with the Upwind scheme here. So it limits the diffusion problem. Okay, it limits the diffusion problem, but this one is slightly, unbounded. Okay, but let's say you have this midpoint scheme. Okay, this midpoint scheme is very much like linear, but you will have this unbounded situation over here. And you have linear upwind as well. Again, a mix between linear and upwind. Okay, you can just, just adjust the, you can just do some adjustment. Okay, but this is unbounded scheme as well. Okay, so no scheme is perfect, but you generally want a balance between accuracy in terms of all these diffusion things happening, and of course the stability. So in terms of accuracy, linear is better at minimizing the what do you call that, the error between actual solution and the actual solution and the the solution we obtain using the numerical schemes. So where numerical schemes tend to have trouble is where you have this sharp change over here, and that's why you have this unbounded situation. So in fact, for our spherical case, we have a very sharp change of temperature from 400 K into a fluid of 300 Kelvin. So originally, of course, I want a 500 Kelvin one, but that kind of introduces turbulence. But you see, there is a sharp change between the solid and the fluid. So generally speaking, you want a solution that will not blow up. It won't oscillate with respect to this normalized distance. Okay, so that you don't have the problems we have when we solve for the solution. Okay, so what can we do? We can actually look at the fvSchemes over here to check which of these divergence schemes are upwind and which ones are linear. And it turns out already over here that most of these schemes are upwind schemes. Yeah, most of these schemes are already set to upwind. So technically speaking, they should be pretty stable. I mean, all of these are linear, but you can change them to upwind. And I did that. I changed every one of these to upwind, or for example, I changed it to upwind, and also changed the interpolation scheme from linear to some version of linear schemes. For example, this is a cell MD limited. So let me take a look. There's this gradient scheme. You can see there's a lot of things that you can tweak around with these fvSchemes. Okay, so for these fvSchemes here, you have these linear schemes, and then you have these gradient limiters. And what are these gradient limiters? Well, remember we try to use this stiff ODE as our benchmark. Okay, we try to use it as our benchmark, and what we have is that we want to prevent this initial gradient from being too sharp. So that's what the gradient limiting scheme is about. Okay, this is a Minmod linear upwind, limited divergence, and where is it? Gradient schemes. Yes. So gradient schemes, you try and do cell limited gradient schemes in case that the way you're interpolating some gradient of the value there. Again, we have to interpolate at the face, but sometimes that interpolation can go haywire because of the instability issues due to a bad mesh I was talking about earlier. So we have a cell limited scheme, multi-directional cell limited gradient scheme, and all of this. So this was the one I actually opted for. So again, you have some cell P and a cell N, and the gradient, if let's say you were to measure it at this point P, it will go up to this point here. If we were talking about it normally, if we were to try and measure the gradient here, it would point up to here normally, but that again may be a little sharp. Okay, it may be I mean, with linear schemes there may be some instability issues. So the idea is to try and reduce the magnitude of this gradient from, let's say, here down to here. Now again, there will be some error with respect to that, but again, it will try to make the gradient not so steep, and hopefully this value is bounded. The gradient is not as steep, and as a result, we get maybe a more stable solution. So that was what I was doing with this Gauss, the cell limited schemes. Okay, the correct syntax is of course this one I'm highlighting here, cell MD limited Gauss linear 1. So plot, and I try the surface normal schemes as well. I try to do a limited schemes, but none of them work. Okay, so I try to do a limited scheme, none of them work. So I was trying a lot of this, and in the case where I did the experiments, it's called fvSchemes experimental case. You can see the VI system, oil, fvschemes.dictionary. I changed everything to Upwind. I changed the gradient schemes to a limited linear. Now this one is called Crank-Nicolson. It is another way of trying to stabilize the time-dependent schemes. Okay. Again, by trying to limit the gradient that the maximum gradient that it can go with respect to time. Okay, so let's see, time schemes is here. Alright, so you of course change the property of the cell with respect to time, and Crank-Nicolson is one of the ways to do it. Okay, so this actually tries to it's the same idea. You try and make the gradient with respect to time bounded or lesser than what you predict, so that the solution becomes stable. And of course, at the expense of accuracy, but at least you don't blow up. Okay, so that's the same idea I was trying to do. So you have this, you have all of this changed to Upwind, and actually these two terms you don't really need. Okay, you don't really need these two terms, and even this one I also try to change it to an Upwind. Laplacian schemes I try to change to a linear limited scheme, and of course almost everything except the interpolation schemes, which there is really no choice. Everything I change to an Upwind scheme or some scheme that actually limits the maximum gradient that you can achieve. After doing all this, none of this work. So your conclusion is that the cell must be, the mesh must be really so bad that no matter how you change the numerical schemes, the solution actually blows up. So that's a reason why, okay, you have to conclude that the mesh is so bad, so you have to look at the way you mesh the thing, generate your mesh. Okay, and of course I was trying to see whether I could take any inspiration from what do you call that? The direct numerical simulation. So I tried that, and they were using a Gauss cubic instead of a Gauss linear scheme. Okay. So yeah. So this is where the numerical schemes for the DNS foam comes about. Oopsie. So CD foam tutorials. And why do I look at DNS foam? Is because they talk about resolving flow instabilities, and DNS does exactly that. But even then, you can take a look at the fvSchemes. This is where we talk about this. They resolve very small flow instabilities. They use Gauss linear scheme, Gauss cubic scheme for divergence. But even when I try that, as to just to iterate and experiment, none of these seem to work. Okay, every time I try to change these schemes, the solution blows up. So I've been doing lots of changing there. I've been going through lots of the syntax as well. And one thing of note, of course, is that when you look at this one, divergent rho new f, dev2 t gradient of u, this one is actually dealing with some stress tensors. Now the thing is that with stress tensors, there's no mass flux actually bringing a stress tensor from one cell to another cell, so that you can't really just do an upwind there. You need to tell OpenFoam, okay, what kind of quantity are you trying to measure that upwind thing with? So I mean, just for the heck of it, I did upwind phi, where phi is the mass flux. Again, it doesn't work, no matter what I tried. So actually, the correct way is to use Gauss linear, of course. But when I was troubleshooting this, I was messing around and trying to change everything to upwind, and trying to change all the gradient schemes to some form of limited gradient scheme. So at the end of the day, what this investigation shows, I mean, I did all the experiments, and all of them, in all of the cases, the schemes actually didn't make too much of a difference when it came to stability. And every time I changed one of these quantities to upwind, it didn't really help, and the simulation just kept blowing up. And yeah, that was quite a frustrating process. But at the end of the day, it shows that okay, a good mesh is important, and no matter how you try and change your numerical schemes, if your mesh is so bad, no amount of upwind scheme is going to help you. So you need to change your mesh in this case, since we have found that that changing fvSchemes and fvSolutions doesn't exactly work. Okay, so vi system oil, okay, fvSolution. So I've changed the relaxation factors to something very low, and I haven't changed the divergence schemes to something very low. I mean, to an upwind scheme. Okay, none of these work. And of course, there is a difference to be said between okay, there's a difference between residuals versus instabilities. So residuals is that okay, let's do a short discussion on the difference. Residuals is that, okay, residuals is that, okay, let's say you have some value y that you're trying to iterate, and this dotted line is the actual value. So maybe you start over here. Now as you try and iterate, ideally as you go along a certain number of iterations, you would hope that the value would converge to some value. That means at the nth iteration and the n plus 1th iteration, the difference between them is small. So the delta y is small, right? So if the delta y is small enough, we would consider the simulation to have converged. Okay. So we can say okay, delta y over delta iteration if delta y delta iteration is small, we can consider this case to be converged. Okay, so that means at a certain time step, we will find that the fixed value is there. We will have a certain fixed value. Now, these oscillations we're talking about is pretty different. So let's say instead of the iterations being what we are measuring at, we have oscillations. Let's say this is the actual one, but this is the numerical one, and we talk about them having oscillations. So these oscillations are with respect to x, meaning to say after you've done the converging of every point, they still result. I mean, after you have converged on a certain value of y at a certain time step, and yeah, let's say this is a certain time step, t equals to 0.5 seconds, for example, and then x equals to 0.1 over here. So let's say you have done all your iterations already, and you found that, okay, the delta y is so small that you have become fixated on a certain value. But yet, as you repeat this process for your whole mesh, you still have these problems over here of oscillations. So this one on the left, it is actually what we talk about in residuals. Well, on the right, this is the oscillations with respect to x that we are talking about because of the numerical scheme. Okay, both tell you that, okay, there's some problem that, I mean, if you don't converge this, you will never actually get a proper mapping of these points in the first place. You'll not be able to generate any kind of field. There's no result because the guesses keep changing. As you increase the iterations, your value of y, which you guess, keeps changing, and we never stop. And the thing about relaxation factors, okay, relaxation factors prevent oscillations happening with the iteration, but they don't help with the oscillations happening here. So relaxation factors actually help here. So relaxation factors actually help here when you're trying to iterate a certain value of y at some position. But after you find that they converge, they still produce these oscillations. What helps here are the fvSchemes, the numerical schemes, which we try to troubleshoot these with. Yeah, they are the fvSchemes. So when we adjust these two, when we try to get rid of these two issues, do remember that there are actually different issues altogether, and adjusting the relaxation factors may not actually deal with this, of course. And okay, so one of the ways is through fvSchemes, because that itself may cause, doing a linear scheme may cause oscillations. Secondly, of course, is your mesh. Okay, so mesh we will talk about in the upcoming videos. So hopefully you understand where all these discussions come in the bigger picture by seeing these explanations here. Okay, so thanks for watching. I'll see you guys next time. Thanks for going with me through this troubleshooting process. It can be quite frustrating when you do OpenFoam and you got to troubleshoot and you wonder what's wrong. So we've gone through relaxation factors. We see that that's not the problem. We tried to arrange the fvSchemes as much as we can, and again, that's not the problem. So the third thing we might want to do is take a look at the mesh. So thanks. Yeah, we'll see about that in the next few videos. Bye bye.